Suppose we're ready. Kick off. All right. All right. Good evening. Welcome to ASQ section. Glad you could all make it once again. We're here once again to have one of our presentations, new exciting event. So we'll go ahead and get started. I guess as we typically do, we've got to get the pointer going the right direction. All right. Once again, we are online this evening, so we will ask that you speak up if you're in the audience trying to ask a question. We've got a microphone here. We're going to try to get it to you, but it is a little difficult for those online to hear if you're not projecting loud enough. So appreciate that, and speakers, if you can restate questions or information that's helpful for those online. Before we bring up Jim this evening, we want to take care of, like we typically do. We'd like to see if we've got anybody here that's new or maybe hasn't been here in a while. Like if you could just stand up, introduce yourself, and let us know what brought you here this evening.
Hi, I'm Steele, and just recently the 34th Street dead engine, and I'm a guest of Jim Steele. So I'm real excited to, just before I left Honeywell, I had a demonstration to the Army on how they were started the additive manufacturing process. That was about 6 years ago. So I just remember seeing that and being absolutely blown away. See what he's going on with respect to additive manufacturing. So thanks for having me.
Well, thank you. Welcome. Do we have anybody else this evening? All right. That's fine. Glad you can all make it back. All right. As we typically do, do we have anybody looking for a change in employment? Maybe like to let us know what you're looking for. Get your information out there. Okay, well, that's encouraging. On the other side, do we have anybody that may have something to offer that you'd like to announce or let us know? Well, all right then. I guess with that, we'll continue to move forward. Anyways, in regards to employment, we do have our career page on our ASQ Phoenix. We also have a job board on our My ASQ community, and we do have a Twitter account also where we post and communicate any openings. So if you are interested, appreciate you taking the opportunity to check those out. Yes, couple of, whoops, whoa, where'd we go? A couple of events coming up. If you are interested, ASQ is going to be offering a Lean Six Sigma training starting next month. It's one of the extended courses, so 4 weeks, but if you're interested, check out the ASQ training site. Also, over in California this fall. They'll be doing their 12th California Quality Conference. So again, we have a link on our site if you are interested. Want to find your way over to the LA area. Certainly some good discussions going on there. I guess ASQ announcements. In case you haven't heard or seen, last week the ASQ has changed the membership status and increased our benefits. So full memberships are now a professional membership. The associate membership is no longer available, but certainly the professional and others are still out there. And there's additional benefits now with all membership levels that include expanded access to the tools, resources, and training that have been developed by our thought leaders and subject matter experts across all of the divisions and forums at no additional cost. So that's certainly encouraging. And moving on to our section, kick off our announcement. I do want to let you know we are starting to plan for 2020. Besides business plans, we got to look at our leadership team. We're going to have some shuffling around this fall, and plan to have a few additional board chairs and committee members available. So if you are interested, either get a hold of one of us that are on the board here tonight, get us your contact information. Also, or just go through our ASQ 0704 contact us at gmail.com. We'll get your information. We'll get back to you with what we've got open and what we might be able to put together. Great opportunity to help the community and give you guys some extra credit and some leadership challenges. So please let us know. Also, moving on, we also just a quick review of where we stand so far this year on our evaluations. We're doing pretty well, but we do want to make sure we get feedback from you. So if you have the chance, get on our website, use the QR code that's on your receipt following the meeting, and let us know what your thoughts are, what you thought of the event, how Jim does, and what else we can do to help. So I guess as far as any of the other officers here this evening, any announcements or anything we wanna bring up?
So far, I think that will be good. Every presenter end of the mind that the data that we collected is not for now.
And Matt.
I want to conclude the consensus.
All right.
Okay.
Just getting through these quick tonight.
Life cycles that running. Let's see, degradation, and these are the RC we've done, and finals we've just, that's what we know. And then, and then we can what we've done here, Jared, that what are the data set, the additional data set to conclude to isolation?
ASQ training organization and training. ASQ training is...
It's not on yet.
Of course, it needs new batteries. Try it again.
Hold it. Oh.
Wow. ASQ training has 11 courses that we're bringing to Phoenix this fall. And I've highlighted all 11 of those on our website with a link to their training catalog. So if you are interested, you want to see more details such as course descriptions, the duration, the dates, costs. It's all in that link. So again, that'll go live here after tonight's meeting on our website. You can also go to ASQ.org and go to their community tab.
All right. Then we will move on here with our member benefit discussion. Just do a quick review of recertifications. Tim?
All right, thank you. Okay, yeah, so I'm Tim Lane, for those of you that don't know me, and I'm the section secretary. And we're going to be talking about getting recertified. So those of you that have certifications, you need to keep those current. So this is how to keep that current. So again, we're all online for this now. So basically, you go to the ASQ website, you go to recertification, and then you can download your, again, a new recertification journal that allows you to start tracking your various activities and your recertification units. And again, you need to do this every 3 years for most of the big certifications. So, like, quality engineer, quality auditor, reliability engineer, all that stuff, it needs to be recertified every 3 years, either by getting recertification units or, horror of horrors, retaking the test. So again, it's important to kind of keep track of this as time goes on so you don't get caught short. So again, this is just a screenshot from the website. And basically, these are just different activities, different kinds of information that you need to know in order to recertify. So I strongly recommend you go in and take a look at this. And, so by clicking on each one, it gives you an explanation of all the different steps and everything. And again, some of the main points. So again, every 3 years, you need to get at least 18 RUs or retake the exam. It's not that expensive, 89 for 2 or more. And it kind of gives you some idea, of kind of your timeline. So you've got 3 years in order to initiate your recertification. You have a 6-month grace period. And then eventually your cert would expire if you did not recertify. One really nice feature is if you have multiple certs, you can actually synchronize those. So you only have to recertify once, to get them all at the same time. I actually have 3 certifications myself, and this has been a big help to, be able to do them all at once. So, it's much more convenient. And again, keep up with it during the 3-year recert period. So don't get caught short, as has happened to me. Because I've actually recertified 4 times now. And, keeping up with it, not getting like, oh, I've got 2 months left and now I've got to go try to take some classes and, fill in my RUs and stuff. So again, be thinking about it during that time. And then I've got a sample log. So this is actually my own recertification journal. And basically, these are all the different activities that you can do that allow you to earn recertification units. So like, for instance, going to the Lean Six Sigma conference this spring, earn me 3 RUs. Going to these meetings, you can get up to 11 RUs now for this. So going to them, 2.5. And then just for being an ASQ member, they'll give you 1.5. So they add up if you keep up with it. And so it's really, really handy to be able to do this online. So again, you don't have to mail it in at the end, and it's reviewed. It's more or less continuous, so you can track your progress. So again, if you've got certifications, it really pays to stay on top of it, and just make sure that you're ready when the time comes. So, any questions or anything? All right, great. Well, thank you very much.
I guess one thing, Tim.
Yeah.
You get a half a point for coming to these meetings, so it doesn't take too long to add up and get the recertifications that you need. So, anyway, thank you, Tim. All right. So, with that, we'll get going here with the real presentation, and just do where's it? Quick. Okay. All right. I just want to thank Edward Jones quickly once again for the facility and the food. Do appreciate it. They've got a great setup here, and all the chance for you guys to be comfortable, and we can talk and converse and really get these activities going. So, as we go forward here, our speaker tonight, Jim Steele, Vice President in Quality and Compliance at Watershed Idea Foundry. Jim has over 35 years has been worked with international manufacturing for companies such as Stryker, Medtronic, yes. Motorola, DEC, General Dynamics. His technical expertise includes additive manufacturing, medical devices, semiconductors, electronics, aerospace. He's led reliability, quality assurance, products and process design, development, manufacturing, engineering, and operations and organizations. After 5 years of consulting, Jim has joined Watershed in 2017 to lead their QA and manufacturing design consulting services, implement the company's quality management system, and characterize, validate their contract for additive manufacturing services. Accomplishments include implemented a robust design control, risk management, quality management systems for international client companies, managed 100+ projects, product and process characterizations and validations. He is a master's MS in material science from UW-Madison, BS Mechanical Engineering degree from San Diego State, graduate of Regulatory Affairs from University of South Florida. He's also a current member of our section and program chair. So, Jim, it's all yours.
Okay, is this working? Is this working? Yeah.
Yeah.
Okay. Forward?
Yep. Oh, you need to switch slides.
Yeah, that would help.
Come on.
So I appreciate everybody coming out and joining with this presentation. Hopefully you'll find it interesting and exciting. As Peter discussed, additive manufacturing is a very exciting area to be in. And I'm looking at a wide variety of manufacturing technologies, and 3D printing is awesome. So hopefully you'll get a sense of that from the presentation. Yep.
Your internet might just come through.
Okay. Yeah, it's just... Is that working?
That's that one.
Okay. You can dress me too. There we go. Okay. Yeah, we had a few interesting technology challenges today, so kudos to Bob for working through all these issues. So I'd like to go over the presentation topics. And so as a medical device manufacturer, we're in an FDA-regulated industry. And the FDA is actually a legal entity. FDA can actually throw you in jail. So it becomes very serious. The people they throw in jail is the CEO and head of RAQA. So hopefully we make good money doing that, but it is, you know, but you do everything right, you're okay, right? It's when they falsify things, people get hurt, that, you know, they really get into it. I'd like to give you a view of watersheds additive manufacturing, and then we'll go into design of experiments. And the old methodology when I first started engineering was we did one factory at a time. Well, there's some limitations with that, and I'll go over that. Talking about main effects, when you talk about design of experiments, you talk about the main effects. There's also something called interactions, and I'll go over that. DOEs actually use a methodology, and so there's a cascading. You go through various steps to really narrow down your process and get that in control and really understand what's going on. In 3D printing, in one of the videos I'm going to show when we talk about HIP, hot isostatic pressing, and so that'll give you a sense of what the process is. So in 3D printing, you end up with a lot of very small holes or voids in your product, and so how we get around that. R squared adjusted versus R squared, again, indication of your capabilities, linear versus nonlinear modeling techniques, and then something that I recently learned was a one sample sign test when the traditional t-test did not work. So to give you a sense of the FDA, the main regulation they use is the 21 CFR 820. They all have it online. It's updated periodically, but that's the overall regulations. So one of the things they talk about is process validation, and that's really where the focus of this presentation on, is to talk about process validation. So it means by establishing by objective evidence, FDA talks about objective evidence that you're actually following your procedures, that a process consistently produces a result, or a product meeting its predetermined specifications. So in your process validations, you're trying to develop what the specifications are to ensure you're getting up with the product you expect to end up that you're processing. So FDA has a lot of guidance documents. If people are involved with ISO, you know you have to buy ISO documents and stuff like that. With the FDA being a government agency, all this stuff is for free. So if you've done the medical industry but want to learn more about process validation, the FDA does a pretty good job with it. It gives you a good sense of how the approach is. And the idea is that if there's problems with your process, you want to find them before you ship the product. And so these processes help you do that. It's a little bit fuzzy, but basically it talks about your in-process control. And so if it's verifiable, so if you're able to measure it or inspect it, those sort of things, then you don't need to do what they call validation. And so, but there's also times when verification can get very expensive, so you may still choose the validation route. And with validation, you potentially have to redesign the process if you're not meeting your expectations. Whoops. So give you a sense, so we have on our big piece of equipment, we have a 1,000-watt laser that we use to melt the metal with very quickly. So now we found the low end on one of my experiments. So we can run from 55 watts to 1,000 watts. Now I have another piece of equipment that's much smaller, and that one runs fine at 45 watts. But when I tried to match the machines, I lost part of my DOE because of it. So equipment capabilities for the big machine is 55 to 1,000, but you hit with too much laser power, you're splattering metal all over the place. It's just too powerful. So your process is in a tighter window. And then once you understand those challenge conditions, where the edge of the process is, where it breaks. You want to understand where the process breaks, so now you can do your safety margins when you design your nominal operating limits. And that's what you're trying to do, is be in that safety zone so the process is very robust and repeatable. Okay. Oops. There we go. Okay. So in qualification, for equipment, they have 3 phases. And so installation qualification is the first phase. And so the question you should ask yourself is the equipment set up correctly, and does the equipment meet its specifications? So if you have 1,000 watts, does it really put out 1,000 watts? With the operational qualification, which is the next phase, is, as I said earlier, where does the process break? And so then, when you understand when it breaks, then you've got those limits, those process windows be set. And then the performance qualification is, what are the anticipated process conditions? So what kind of variation you can have with your material coming in? What kind of environments? You know, like I work in wafer fabs with clean rooms. Obviously, you got to keep those very, very clean. And then, does the process produce product that meets this predetermined requirements? One of the things that I really appreciate, since I got into the game a little bit late, is the FDA has really endorsed or investigated, I guess is probably a better word to say, because more and more medical device manufacturers are going into doing additive manufacturing. Additive manufacturing has actually been around for about 30 years. For the last 10 years, it's really started to take off. And so I know with one of our suppliers, they spent almost 2 weeks going through their technology to understand that. So they work with the industry and put this guidance together, which is very helpful as I'm putting together my performance qualifications to do that. And so then you have a simple flow in here. And so you have the design portion, material, which is the powder and argon, is the main materials you use in the process. Lots of work on software. And you know, recently heard about the airplanes with the software problem. Well, equipment can have problems with software too. And there's a big effort with what they call software validation. Then you have the build, or what I call fabrication. And then afterwards, you have some cleanup, some ripping off supports, variety of other things. And then how do you know your product's what you expect it to be? Okay, introduce you to my company. We're sort of schizophrenic. We do consulting along with setting up additive manufacturing. And that's actually been my boss and my really focus for the last year, is to get this manufacturing area up. And so we actually have, we purchased 2 powder bed laser melting systems, and we use titanium 6-4. And titanium has, the 6 is aluminum and the 4 is vanadium, and that is biocompatible. So very few people are allergic to it. Now, I work at Medtronic, and I don't, they still do that. But if somebody was allergic to titanium, they actually gold-plated your pacemaker for you for free. I don't know if they do that anymore, but obviously very customer-focused. And so we also are involved with some existing businesses, and we do something called structural coding, which is to put the serial number, basically a code into the device. You can do X-rays, and so you have traceability on the whole history of that device. Just those basically pins with little cutouts. So the 3D printing slice software has some really nice advantages. So in subtractive, you start off with a block of metal, and you remove metal that you don't want. But obviously, you have to get into those, have access to it, to be able to remove the material. 3D printing, you're doing additive, so you're starting from the base up and building layers as you want. So, manual mess repair, when it transfers to computer-aided design, they can do part hollowing. That's why aerospace absolutely loves it, because they can actually increase the strength and reduce the weight. And aerospace, big deal. Complex lattice and optimization, you sort of get a sense of it. We can make very detailed surfaces. And so on spinal implants, when you put those in your back, the doctor puts in your back, you don't want to slide back out again. And so we put a surface on there that adds friction, basically, so it stays in place. It also, we do the manual supports, and so for people online, there's some posts at the bottom of the device in the upper right-hand corner, and that's what actually supports the device as you start making 3D prints. And then we do deformation, predictions, compensation. It's under a lot of stress associated with it because we're at very high temperatures. And then there's a heat treatment simulation to see if it will address some distortion issues. And then they also predict it when you remove the supports. It's all high stress. What's it going to warp? How is it going to reform? Here's a picture of our corner of our manufacturing area. We basically have we have a smaller unit on the left, which is our Mini, and it has a smaller build plate. That's where you basically build the components on the build plate. And then we have the one, which is our big system. And unfortunately, our video didn't work, but it would have shown you the size of it. So this is much taller than I am, the big machine. So you get a sense of how big that is. This background is looks a little smaller than it is. So go ahead and see if we can do the video. So I had to find another video just before the meeting. Get to work? Yeah, I thought it was. You get the video up or not?
The first step of our additive manufacturing process is 3D design. I'm showing on my screen.
Okay.
Modeling and processes, so we can take the virtual design and simulate our process in the computer, verify the designs are going to work as intended. So once we validate our 3D design, we will start by printing that in plastic. This is a relatively quick and inexpensive process that allows us to give us an actual 3D part versus a virtual design.
You just want to hold your computer and everybody will look at it? There we go. Okay. Sorry about that. Okay. Well, online people, it's a pretty interesting video, so maybe we'll send them the link. They can look at it later.
So the first step of our additive manufacturing process is 3D design. Our designer will either create a new design from scratch or take an existing design and add features that take advantage of 3D printing. They have the capability.
Whoops, you lost the video.
So we can take this virtual design and simulate our process in the computer, verify the designs are going to work as intended. So once we validate our 3D design, we will start by printing that in plastic. This is a relatively quick and inexpensive process that allows us to give us an actual 3D part versus a virtual design. We're in our additive manufacturing lab at Indianapolis, Indiana, next door to our powder facility where we make the analyzed powders using 3D printing. This printer has a 400-watt laser. A doctor will carry the powder across the build plate. The laser then goes down and selectively melts or centers the particles together to form a solid part. And then this process is built layer by layer. The key advantage of additive manufacturing is the reduction in raw materials needed to process the part. Because only the powder that's needed for the design is used. The remaining powder is captured, working with our powder facilities, we can actually recertify these powders as needed. Once we have printed a part either in plastic or more importantly in metal, we can scan the part and measure the dimensions and validate that we met the criteria for design. Additive manufacturing allows for complex parts that cannot be manufactured by traditional machines. This allows our customers to be very innovative. They can create designs that work possible and fast, and this can lead to improvements in efficiency, cost, and performance.
All right. Good job, Buck. So one of the other things I didn't mention is the ability to reduce the number of parts. So with 3D printing, you actually take 5 or 6 parts interconnected and remove the supports, and now you got a fully assembled device in 3D printing. So we actually did our first one last week. Hey. Okay. So we did our first, we call dynamic part. So we were actually going through secondary processing for that right now to finish that up, but we're really excited about it. Did we lose it?
All right.
Technology. Okay, you're going to be my... Yep, I think. Next. Okay. So I talked about hot isostatic pressing and also traditional heat treatment you also use in the devices. And so the typical pressures they get into is 1,000 to 2,000 bar, or 15,000, 30,000 psi. Oops. Temperatures up to 2,000. And what you're actually doing is you're taking the temperature just below melting, because you're trying to move atoms around in the device to get rid of those voids inside the device. And so they basically press them out. So if you have a lot of porosity in your device, you're going to end up with a lot of shrinkage. And so one of our goals when we designed the process was to try to avoid doing hipping, because it could be 2 weeks turnaround time that we have to wait for the product to come back to go through the HIP process. So we strive very hard to get the porosity down to a very small percentage. With HIP, you can hit 100%, and I know that's for a fact because I've done it. Whoops. Did I do some? Okay. Yeah, I'm still not controlling it. Okay. Oops, he went the wrong way. Okay.
One slide here and one slide there.
Really? What do you got up here? You got the wrong slide up.
I know I do.
Wow.
You want that slide?
No, actually I want to do the HIP video.
Oh, the hip video.
Yeah.
Oh, now you're going to throw another curve in.
I know. I can explain it, porosity. Okay, so. Okay.
But because of this personal freedom.
Oh no, you got two videos going. Okay, try to start it over. Sorry about this, guys. Okay. Yeah, here, you can hold on this one. Useless to me, this one.
We must minimize the risk of inconsistencies with our materials in order to be able to take product quality for granted. Materials formed from casting or additive methods such as 3D printing contain porosity or microcavities. These porosities must be reduced to eliminate the risk of premature breakage. This is usually done in 2 steps. Firstly, heat is applied under pressure in a HIP process which reduces porosities and cavities. Secondly, the material is heat treated in a process where rapid cooling improves the fatigue and ductile properties. It would be a disadvantage if these processes could be combined to save energy and increase productivity. But combining quick cooling with high pressure places stringent demands on the pressurized furnace. The vessel needs to be robust enough to withstand the high pressure, while also being cooled quickly from the outside. By adding a wire package to the outside of the vessel, both can be achieved. The wire package allows the inner wall to be thinner for quicker cooling, which maintains structural integrity of the pressure vessel. The thinner wall enables a unique heat exchange system, which makes it possible to cool down the load quickly and meet the requirements of the heat treatment process. This means that the HIP process and the heat treatment can be run at the same time in the same vessel, saving time and energy. Through the Quintus Uniform Rapid Cooling System, URC, the hot gas is pushed towards the thin-walled vessel. At the same time, the vessel wall is cooled by water from the outside, while it is supported by the wire package to keep it safe and under control throughout the process. With this unique combination of HIP and heat treatment in one, the load only needs to be heated and cooled once.
You can probably stop that, Bob. Just go ahead and stop. Yeah, I think at this point, you know. So, but what, you know, part of the thing was understand porosity, and again, that was our goal, is to reduce the porosity within the device. So let me get into introduction to interactions. So in traditional linear responses, you have a okay. Yeah. Go back to the cubes.
Where do you want?
Right there. Yeah. The cubes. Okay. So this is a very early version of our cubes, and we started off with cubes. So the technology with cubes with basically through holes. And so a lot of things, holes are very challenging because basically when you're doing 3D printing, you're actually making a series of triangles is the way the technology works. And so trying to get a nice curved surface is very challenging. So we started off with building cubes. And so you can see the one on the left has, you know, you can see cubes don't look that good. It's a little bit dark here, but side holes are really bad on this one. And then as we learned the technology, learned the factors that affected the quality of it, we ended up, you can read the M6, with the other one you can't read the number. We had holes that are not perfect, but they're pretty close. Okay.
What's the size?
Those are 10 millimeter by 10 millimeter by 10. And so the smallest hole I think was 0.02. So when you get into design of experiments, so traditionally back in the day was you did one factor at a time, you did the dial up and down, you saw what it was an effect. Well, one of the issues you're not able to detect is some factors are actually interconnected. And so you'll miss all the interaction effects. So by doing design experiments versus one factor at a time, it's much more efficient, get high precision, understand the main effects, the big ones, and then you also see the impact of interactions. And a lot of processes have interactions involved. Okay, oops. Okay, so traditional model would look at, here's the, you know, constant plus AX and BX. And so what that basically would do is you'd have a parallel lines. And so if you have parallel lines at two different settings of the two factors, you end up with, that's the technology. But a lot of things have an interaction. So if you look at this one on the right, you have A equals 0, has a smaller slope than A equals 1. And so what you look at in the plots is whether the plots will cross each other. And so that one will cross, and it does have an interaction factor. Okay. So here's one, stroke survival rate versus treatment. And so this one actually has both. So for a severe stroke, your drug does not have an advantage over placebo. But for moderate and mild, you have a much higher survival rate. So that helps the company know that for this condition, the drug's not value added. For these other conditions, it will add to the quality of life. And so using the cookie baking as an example, when you look at the main effects, and so the p-value you're looking for something significant, medical device usually uses 95% confidence, or the p-value is less than 5%. And so here's an experiment on cookie baking, and the p-value here is 0.91, which says these factors by themselves have no predictability, basically. Okay? And so, but if you look at the plots, you see here that high temperature and short time get you good cookies, or low temperature and longer time gives you good cookies. So what would happen if you had high temperature and high time? What would happen to the cookies? They'd burn, right? Or if you do it too short, it's not fully baked. So makes sense. Go ahead. So this one, again, we're looking at the main factors, temperature and time, and that's not what's driving this process. It's the interaction, temperature and time. And so if you don't understand, you look at one factor at a time, you're not going to detect this. In a lot of processes, you can miss something very important. Okay? So full factorial design of experiments. So you have the number of levels. So you have -1, 0, and 1, so high, medium, and low. And then the number of factors, input factors you're studying. So if you want to just look at a 2-level, 3-factor full factorial, 8 parts or 8 runs or whatever you're doing for your DOE. And then with that, your main factors are A, B, and C, but then you have all these interactions. So there's an interaction potentially between A and B and C, B and C, and ABC. So as you increase the number of factors, obviously this gets very complex pretty quickly. Here's one what they did on bearing life. And in the technology they did, there was an interaction that they did not detect for decades, that they didn't know about. So go ahead. And so what they were looking at was oscillation and heat. And it wasn't linear. It was actually, if you controlled both of them at the same time by raising it, you didn't get just double, you got 5-fold improvement in life. So, go ahead. And so, 5-fold increase, and they were missing a very important interaction that was going on. Okay? And so, bearings have been around for decades, right? And this, because of the approach, design experiment approach, or lack of, they didn't realize this improvement was occurring. So, again, the engineers, that's what they were taught, right? 1 factor at a time. And so, the interactions, they didn't see. And so they missed a very, very crucial improvement in the process because of it. So, starting off, your technology, you've got all these factors. Actually, one of the scary parts with this equipment, I can actually control over 100 factors on this piece of equipment. The equipment we have is actually research equipment, not production equipment, which I would have voted different. I wasn't with the company yet before they selected the equipment. So how many parts are needed for a 3-level 8-factor full factorial? 6,500 parts. Okay? So now it's not very cost effective yet, right? So this is where we talk about the methodology. So I'd like to introduce you to coefficient determination if you haven't seen this before. And this basically it gives you a sense of the strength of your predictive model. And so what they do is they take their data points of actual, they try to fit a model to it, and then the difference is your amount of error or lack of predictability. And so the traditional one they look at is R², but there's a condition with R². With R², as you add more and more and more factors, it improves it, or appears to improve it. So if you're looking at 8 factors, you add more interactions, you add all those in there, it'll improve the technology, or the prediction, sort of. But actually what they've done, this is probably a few decades old, on R² adjusted, and so with R² adjusted is really giving you a much more accurate value, because if the factor that you added to the equation doesn't add more predictability, you take it out. And so for medical device, usually 70 or 75%, that 75% of the model will predict the accuracy there, and if you get over 85%, I will use that as a predictive model. And so here gives a sense of a 3-factor where I include the 3 interactions. And you see that the R² at the top one is 95.5. The 4 main factor one, that's 89%. But look what it did for R² adjusted. So what this is telling me is that interactions is not a big deal with this process, at least a particular one. Okay, so what we start off with the screening design of experiment, and you usually do 2 levels in high and low. And then, but because we talked about interactions, all those things are all sort of grouped together. So when you do a screening experiment, you cannot delineate between interactions and the main effects. They're all grouped together. And so what that does is with 8 factors, I can do it in 12 runs instead of 6,500. But you understand this is the first step, right? Understanding, and so it could be an interaction that's causing it, or it could be the main factors that are driving this. But you're just trying to see what of the knobs will cause everything to jump, right? It's sensitive to that. And then I always put in center points because a lot of processes are not linear. They're curvilinear. And so that also by throwing the 4 points in the middle, I get a sense of sort of the variation in the settings. And so, and then, you know, we put that into a multiple regression model. And so, go ahead. A little hard to read, but here's the sense. So I've got 12 that are involved with the factor, Bracken-Berman, and then I have the 4 center points. These are all randomized, the order's randomized and stuff like that. So just give you a sense of the high and lows. And this, I showed 3 here, but there's actually 8 in the table. Okay. And so with this one, the Hatch porosity, we, you know, R squared was 87%, R squared adjusted, pretty good, 73%. But what it shows here, so if the constant is below 5% or 0.05, it says that your model 0 is not your y-intercept, is basically what it's saying. So, but Hatch power, Hatch speed, and then Hatch distance. So let me describe that a little bit. So what the hatches are is, I don't know if we picked, no, I guess we really didn't see it in the video. My video would have been there. But we actually do an outline of the laser before we do the inside, because it sort of encases everything in there. But the laser goes back and forth and back and forth. And so obviously it's a round item. So that's why you do this outer loop, contour is what they call it. And so then you got that very linear. And so how far, so when you hit the laser, it actually melts. And so we're going to go to the next one. Okay. And so as the laser's going down, you actually, it's expanding, going down. You have to do an overlap here, because if you don't, you have powder there, and then you've got everything fall apart, right? And so you have to melt in the next layer, but you want to melt too far down, because then you're losing a lot of energy and stuff like that. So this is basically lasers going across. You've got powder here, and then as it melts, it develops this, and it cools as you go by. Okay. And so one of the things that I was involved teaching at UTEP and work with their facility in 3D printing. And so people, I think they were in Slovakia. But laser power over Mach speed over Hatch distance, and layer thickness is how thick you melt it to. And so that seems to work in a lot of predictions fairly well. Yeah. Oh, excellent question, excellent question. So what we do is we actually pump down the machine using argon. And so we were able to get, so a lot of our competitors are using about 100 ppm of oxygen, because, you know, titanium is very, very active with oxygen, right? That's why it keeps it shiny. So we actually go down to 25. And so in that environment, you're not going to create too much oxide. Good question, very good. Okay. And so we did the screening experiment. You sort of know what the big knobs are, right? And so with the fraction factorial, it's another stage in the methodology. And so one of the things that leverages is sparsity effects. So AB interactions, BC interactions, those type of interactions you see all the time. But the ABC, ABCD, those don't happen too often. So fractional factorial takes advantage of that. Again, there's some things that will violate that, but most items don't. And then the DOE is a defined amount of resolution. So again, we have mixed factors with the interactions. We have main effects independent. So you're getting a little more separation there, but it's not the full factorial. Full factorial is able to delineate all the different interactions and all the different factors. So one I went after next was a 4-factor run, and it's the third level, okay? Resolution 4. And this is actually a cross-section. And so on the far left, far right, your left, that's the edge of the cube. And then there's a section called the hatch, which is the center section. And then we have what they call stripes. There's edges. So this section is one set. And this section over on the right is one set. And so what we learned fairly quickly was we don't want those inside edges. because it's a lot of porosity there. And this is pretty high porosity, and this is very early. Okay? And so we did a porosity fractional factorial. And so with this one, again, the constant is significant. Laser power, Mach speed we've seen before. We have an interaction there. But because of the fractional factorial, I can't tell the difference between an AB or a CD. So they're connected together. They're mixed in. But if I look at AB, laser power and Mach speed, I'll put any money on that's the interaction I'm actually having, is AB. Because many factors that are significant, most likely the interaction is too. But you don't know for sure, but most likely it is. Okay? Then we did a top surface one, and so we had stripes as the main factor for stripes, were the main factor in causing the fractional factorial in that zone, that middle zone I was showing before. And again, the constants there. But that shows, so different responses can have different factors or interactions involved. We've gone through this before, so the next DOE was the 3-factor 8 run, which we talked about very early, full factorial with the 4 center points. And so with this one, we're dialing it in, right? So the R squared is now, R squared adjusted over 90%. Laser power still comes in. And this time, AC came in also as an interaction. And so that's a piece there. And if you look at the values, the hatch distance is a lower value. It's still not significant as a main effect, but that would be understandable. That's the interaction. So the final approach you have in the DOEs, a series of DOEs, is doing a response surface methodology. And so if you have indications that you have curvature in your responses, then the response surface is sort of endpoint. If you don't, full factorial is your endpoint. And so it gets into your second order polynomials. So DOE design. So we're going to do, basically think of it as a cube, and you've got points on the corners, you've got points in the middle, and so this is, it gives you a sense of all those interactions. And then also I threw replicates to get a sense of the variation that's going on in the process. And so with this one, R squared adjusted, not quite as good. 78% still is good, and laser power is reigning the day. So laser power, laser power, laser power. And so that's the main one you want to control. But you, again, can improve things by understanding the other factors and how they contribute. And so here's the response surface. And so what we want is porosity. If I run the process over there, I get really lousy porosity at the top. But there's a little blue zone at the very bottom, and that's where I want to be. And the bigger that donut is, you have more safety factor in your process. So that's where you want to be. Okay? So understand linear versus nonlinear. So again, this is just one factor. So I don't have to worry about the R squared adjusted for one factor, right? And so I do a linear, you see the points, and the R squared is 37%. Not very good. But if I look at a different response, go ahead. Get things a little better. Okay? I doubled it, right? But it has this kind of strange zone here, right? You can't have negative porosity. So again, you're still learning about the process. Look at some other responses. Now you've got a response where all the points are above 0. So it's either a third order effect, or even in fourth order, again, doesn't bite you much because, again, it goes in that negative zone. But it's saying, hey, you still want to be in this bottom zone where it's near 0. So you don't know if it's actually jumping up or it's leveling off. So paired t-test is a traditional test that quality engineers use when they're comparing pairs of, so you have one device, the other device, here's the combination of those. And so you have them pairs. Here's the t-test. And so you do your null hypothesis and the alternate hypothesis. And so go ahead. And so with the software I'm using, it says, normality ain't so good. So maybe not normal. It's got the, it's saying not very robust. It also has outliers. There's one on this one, but other ones have much more outliers. But it does do random. So it's saying we need to do another approach. And so that's what got me into the non-parametric tests. And so what they do is they do one sample sign test, and they're basically looking at the median. And so it's not sensitive to the edges. It's sensitive in the middle. So if you've got this really long tail on your normal distribution, this isn't affected by that. So what you do is you say, hey, I believe the median is about 23.7, which is group 1. And so group 1, group 2 is very different. Okay? If it was the same, you would have sort of 5 and 5, right? Maybe, So the 2 here, these groups are significantly different, with these other groups, and the one at the end is also different. So you understand that, then you go investigate why those are different. So hopefully, giving you a sense of process optimization. And so you got validating the equipment. It's IQ, OQ, PQ. And so that's key deliverable for the FDA. Obviously, you can look at that. Designing experiments has many advantages over the one factor of time experiments. Generally, 2-factor interactions are fairly common. And then doing a cascading DOE where you start off with many factors and you're down to the main factors and the interactions. And then the energy density, I continue to reinforce. That is a very good prediction. Okay. We were able to get less than 0.1%. Actually, they can't measure the porosity on our products now. So we have made a decision for implants, we'll still HIP, just because the FDA likes it. But for instruments, we don't have to HIP. So we made a really nice breakthrough to get to 0.1% and less than that. You got R-squared adjusted. It's a better measure of predictive strength. And then you can use nonlinear regression techniques to improve your models. And then the one sample sign test actually is very efficient. I like using it. So, okay, over the traditional T. And then we have densities up to 99.99%. You've got tensile strengths of almost 1,000. Yield strength over 800. And then one of the things with medical devices, you want it tough. So they look at elongation, that it doesn't crack because of the elongation. So you want it in your body to be tough and actually a little bit of flexibility, which you're able to build in with 3D printing, which you can't do with subtractive. So here's a sense of what we've done. We do the big machine with states, and we do the little machines with the capitals of the states. So those are interconnected. So Phoenix and Arizona have a lot of crossover of combinations, but slightly difference between the two machines. Yeah. Yeah, go ahead. Yeah. Oops. Yeah, here we go. Yeah, we went through that before.
I was wondering if you do it.
We do torsion testing, and so that's the main one we use. But right now, at the stage we're in, we're just doing, basically breaking. So we have a sort of hourglass-shaped device, and then they pull it to where it breaks, and so that's where you're getting your tensile information. So we're at that stage right now. But yes, you want to have the toughness, and so. But in your body, you're not going to have too many impacts, unless you're a football player, right? But I doubt if you have a spinal implant, you can be a football player. So, but yeah, it isn't a big problem. But for other technologies, it may be. Okay. Okay. And then I had a lot of help. So one of my friends from, I actually knew him in Dallas, but he's now in Houston, and so he's my. I've been blessed with very good statisticians working for me, but I'm not a statistician. I don't know a lot about it, but I'm not a statistician. John is an amazing one. We also did work with our test house, and so they did a lot of the porosity analysis for us and continue to do that. And then I use Cisco software, and because I've taught universities and also consultant, I get it for free. So it's got a nice benefit, so I thank John for that. Okay. So thank you. Appreciate it. Yeah, got some questions?
Any questions?
Well, okay, Tim.
Yeah, so I was wondering, when you do the compression treatment at
Mm-hmm.
the end,
Yep.
does that come up for like, changes in, say, tension?
Absolutely. Absolutely. So again, you've got all these little voids in your device somewhere, right? And so with the hip, you're just under melting point, under high pressure, and it's squeezing out those. So obviously towards the center, you may not be able to squeeze it all the way out, right? So we actually found a critical where if we were above 1.6% porosity, hip didn't help as much. If I was under that, then I could get pretty close to 0.1 or 0.2. So the hip would help that. But at 0.1, hip's not going to buy me anything. It's not going to improve it much. Yep.
No question on
that. Okay. What?
No question on
Okay. Anything else? I'm keeping you from the evening. Well, I appreciate you coming out and listening to me. Thank you very much.
All right. Jim,
yes?
I do want to thank you.
Yep.
Here you go. We'll give you a certificate.
Yep.
Thank you very much.
Like Barbie.
We also have one other request here.
Yep.
If you could draw a tag for one of our.
Okay, so it's a big number. Last three digits are 000. There we go. Congratulations.
All right. Congratulations. All right. With that, I guess we'll be wrapping up here. Again, a reminder, please take advantage of your certificate and give us some feedback. Use the QR code. Go online. Fill out a survey. We streamlined it, so it's only a few questions now. It should take less than 5 minutes. Also, reminder that next month the meeting's early. It's on the 8th. It'll be again here, and our speaker will be
yeah, that's okay. I've gone through before.
It's going to be talking about constrained line blending optimization.